First of all, many thanks to CSR conference, academic conference, to give me a chance to have this presentation. I'm Li Hui from the University of Electronic Science and Technology of China, currently serving as the Dean of the School of Aeronautics and Astronautics. Here, this is a picture of the UESTC. I think it's very beautiful. Also, I think our university has the most beautiful campus in China. UESTC is located in Chengdu, Sichuan province. Sichuan province is in the western part of China. I think Sichuan province has many beautiful mountains and rivers. I guess somebody know Jiuzhai Valley. Jiuzhai Valley is world famous sightseeing. And also Sichuan is the home of panda. So I hope all of you have a chance to visit our university and the Sichuan province. Here, my talk divided in two parts. The one is review of the development for China's aerospace, and the second is the Miso Rod control system based on digital PWM. And then I will begin my first part. In fact, China has made great progress in space activities in the past 2019. For example, China's space activities have grown rapidly, making the first in the world last year in deep space exploration, and lunar exploration team successfully landed a probe on the back of the moon, and the lunar rover has been working on the moon for 660 days. China has also made progress in remote sensing satellites. For example, the Gaofen 3 and Gaofen 4. And also, for example, the Gaofen 3 satellite has 12 imaging methods with a designed life of 8 years. Look here, this is the space activities in 2019. Okay.
Oh, sorry.
Sorry.
No problem.
Okay. So please wait a moment.
Yeah.
Because network problems.
Okay.
Are you sure?
Yes.
Yeah, perfect.
Okay. Perfect?
Yes.
Okay. So, in fact, China has made great progress in space activities in the past 2019. For example, China has space activities have grown rapidly like this. You can see China is here and Russia is here. Okay. Also, in deep space exploration, the lunar exploration team successfully landed a probe on the back of the moon, and the lunar rover has been working on the moon for 660 days. China also has made progress in remote sensing satellites. For example, the Gaofen 3 satellite has 12 imaging methods with a designed life of 8 years. So look here, the Long March series rockets play a vital role in China's satellite launching, deep space exploration, and space station construction. Up to October 2020, the Long March series rockets completed 350 launch missions with a successful rate of 95%, 14%. And the Long March 5 is the newest model of the rocket in China. So this Long March 5 have the total mass of the 53.7 meters here. And its carrying capacity can reach to 25 tons. On May 5th, 2020, the Long March 5B completed its first flight mission. In addition, China is also one of the 3 countries in the world with such a large carrying capacity. And here, China's satellites are moving towards the diversification according to ground observation goals, as the figure shows, like this. We have developed resource exploration satellite 资源, okay, here, and ocean observation satellites named 海洋, okay, here, and high resolution observation satellite named 高分, okay, here. Weather observation satellites named 风云. Here, the Beidou 3 satellite navigation system provides all weather, all time, high precision positioning, navigation, and timing service for global users. As this figure shows, it provides 2 service methods, open service and authorized service. The open service is to provide free positioning, speed measurement, and timing service in this service area. As the table shows, position accuracy is less than 10 meters. The timing accuracy is 50 nanoseconds, and the speed measurement accuracy is 0.2 meters per second. And in June 2012 and June 2013, the Sunzhou Line here, and the Sunzhou 10 spacecraft were launched to dock with the target spacecraft Tiangong-1. The Tiangong-1 target aircraft is the first self-developed spacecraft of China. And this is Tiangong-2. After the successful of the Tiangong-1 and Tiangong-2 space laboratory is the second space laboratory independently developed by China, which is used docking technologies and conducting a series of space experiments in September and October 2016. The Tiangong-2 Space Laboratory and Sunzhou 11 were launched with the mission of carrying out science and technology experiments in space. Nowadays, China has mastered the technologies concerning astronomers' mid-term stay in orbit and long-term ground mission support. And here, China's lunar exploration project is named Chang'e Project. The Chang'e Project is divided into 3 phases: unmanned lunar exploration, landing on the moon, and constructing the lunar base. The Chang'e 4 probe consists of a lander and a rover. This is lander, and this is rover, okay? And the rover is named E22 as the world's first spacecraft to patrol and detect a soft landing on the back of the moon. Its main task is to land on the surface of the moon, continue to scientifically detect information on lunar geology and resource in a deeper and more comprehensive way. Okay, you may be wondering why China has made such great progress in the aerospace technology. Okay, I can tell something to you. There are more than 30 universities and colleges in China that have disciplines in aerospace, and each year more than 14,000 graduates in the aerospace field are trained, and there are more than 300,000 employees engaged in aerospace-related work. In addition, the Chinese government also invests a lot of resources to encourage innovation jobs. As a result, China's space activities can rapidly increase. UESTC I worked for also has a school of aeronautics and astronautics, which train a total more than 300 graduates in the aerospace field each year. In fact, I have worked in this field for more than 20 years. And so far, I have taken charge of many industry and government projects. By the way, I sincerely invite all of you to come to China for academic visit, exchanging scholarships, or studying for PhD program. Okay, next I will introduce one of my past work, Miso Rod control system based on digital PWM. So I got a model of this, okay, SCAD, that's very famous Miso in the world. So in the past, the rotor control system of Miso often used analog control system such as the SCAD. And nowadays, the control system seems to gradually become digital control like this. Even the Miso servo control system has been developed rapidly, but there are still some problems when it applied in high-speed Miso Rod control system or high-speed flying object. I think it's hard to have a good performance for a control system. So the first, I think, is adaptivity. It needs to operate under various harsh environment conditions, dynamic and static. The response speed of the system is required to be fast, and the linear range is as large as possible, and the zero position is accuracy and torque. So the system must be able to output large enough moment. Else, and the volume, quality, and cost of the system have certain requirements. So look here. The model of the permanent magnet DC servo motor, PMSM, is shown like the figure 4, and the voltage balance equation can be obtained from the Kirchhoff voltage law here. So the control of the PMSM is generally based on PWM control, including PWM control that enables forward and reverse motor rotating, and PWM control that can only rotate in one direction. Reversible PWM control includes bipolar control, unipolar control, and restricted unipolar control. So we used unipolar control for device. So servo system control algorithm includes system position loop, and the feed forward compensation position control used mixed fuzz PID algorithm. Speed control used integrate separate PI control. Feed forward compensation use PD control, like this. Mixed fuzz PID, integrate separate PI control and PD control. We use different algorithms to get better performance. So the position loop is as the outer loop of the system determines the response speed of the servo system. In order to obtain excellent dynamic performance, this system position loop use a appropriate P control algorithm. The corresponding algorithm expressed in shown at figure 6. This is the expression of the algorithm. The introduction of the negative speed feedback is to ensure that the motor can run smoothly at the desired speed. The use of the variable speed integral PI control algorithm on the servo system velocity ring helps to meet the requirements of the system on the rate, speed, and other indicators. the given signal of the system speed ring is the output of the system position ring. The speed feedback signals is estimated from the difference between the position feedback signals and adjacent sampling periods. This is the expression of this algorithm to speed loop controller. Okay, the hardware structure of the system is like this, consisting mainly of digital signals processor, position feedback power device, DC servo motor, and 28 voltage of the source. Like, look, this is the hardware chart of the rudder control system. And the power module is very important for the whole system. The structure of the system power module, like this. In addition to the H-bridge can directly use 28 voltage, other parts like the module of isolated drive circuit needs the support of 15 voltage isolate conversion module. The 12 volt non-isolate conversion module can support the operation of the modules of the position sensor, voltage conversion, and filtering circuit, main control chips, and AD. In one word, the power supply system is mainly responsible for the different voltage power supply requires of each module of the rudder control system. So a little bit complicated because we use many different power supply for different modules. And H-bridge, the DC-DC PWM converter, which is under 4-quarter operation, is adopted in power converter circuit as shown in this, okay? Rudder can start and stop quickly and realize the forward, reverse, rotation easily, a duty circuit, okay? Duty circuit. In restricted bipolar control model is divided into 4 states. Starting state, current follows the loop 1. Excuse me. So 1. The next state is the freewheeling state. The armature current flows along the loop 2 through VD2 and through VD2 to VD3 for freewheeling. The third state is braking state. The current reverse follows the loop 3. The last state is the regenerative freewheeling state. The current is continued along loop 4 through VD4 and VD1. The current directions like this. Under the restricted unipolar control, the current looped in much the same way as the bipolar model. The only difference, the switch that control each stage in the forward turn-on phase, VT3 is off and the VT4 is on. In the reverse operation phase, VT3 is on and VT4 is off. Okay, the current flow direction like this. Okay, that's the duty cycle. Anyway, the advantages of this approach are low switching frequency, optimize the dynamic performance, reducing power losses, improve reliability and safety. Since there are a large number of the interfering signals on this circuit, it is necessary to filter the signals. The hardware filter is implemented by an active low-pass filter, in which the given and feedback attended shift voltage are filtered and feed the AD interface. The hardware structure circuit, cutoff frequency, and filter quality factor as shown in this figure, okay? So we also developed a digital failure. Digital failure requires software to implement it. There are three kinds of filter techniques: impulsive average failures, as in the first formula. Smoothing average failure will add 1 to end of the queue and subtracted 1 from the beginning of the queue. The workflow of the compound digital failure is as follows. Step 1, sampling n data from a queue. Step 2, ranking n data from the smallest to largest. Step 3, sampling 2 data and add to the queue. Step 4, ranking n plus 2 data from the smallest to the largest. Step 5, excluding the maximum and minimum values from the queue. Step 6, calculating of the arithmetic mean. Then the procedure return to the step 3 like this, the logic flow. So the software, the main program assistance software is only responsible for the initialization of the module and the configuration of the globe variables. During system operation, the software waits for the MOSFET to power up in a dead loop and then moves on to interrupt service subroutines that sample the serve control algorithm execution and position feedback signals. This is the overall chart of the whole software system. Okay. To verify the performance of the system, we use the test of error test of zero position, dead zone, symmetry, transit response to check indicators of the system. This is the test results, just like the 3 table. This is the data. The test of the transient response shows the response of system is fast and precious. Okay, just like these curves. And we also compare the amplitude frequency curve, okay? The frequency curves and phase frequency curve between bipolar and unipolar. They are shown that the amplitude frequency curves and the phase frequency curves are smooth and stable, just like this one. This is a bipolar, I think it's not so good, this curve. And the unipolar, you can see the curve is very smooth. So here, the rudder and the functional module used for physical device are shown in this figure. And this is the rudder, and this is the different modules we developed. We even developed a test platform to test our system design results. It's looking very complicated, okay? So, conclusion. Based on the experiment conduct above, we conduct that our servo controller has high performance in motor servo control system. The fast response, strong robustness, high stability, and precious control demonstrate the outstanding performance of the servo controller. Okay, that's all my presentation. Thank you very much. Any questions?